basics. Now, a lot of installers, when they see this, they think to themselves, well, I know twisted bit cabling, I install it. You can't teach me anything about it. But it's surprising some of the things, once you get into the theory of twisted gear and how it works, some of the practices we use make perfect sense as to how we put in the cable. Alright, so we're at optimal standard.
Hi, Party Cube.
You can think of bandwidth as water flowing through a pipe. Okay? So think of the pipe or water that's going to flow through that pipe. If we have a good throughput, then we've got high bandwidth. So basically, bandwidth is capacity. The more bandwidth we have, the more capacity and data we can push through that cable. If we have problems with the cabling, if we have data that can't make its way through, our bit error rates go up, and that affects our bandwidth. So we want less bit error rates, we want more higher capacity in the cable. So how do we achieve the highest level of bandwidth possible? Correct installation is going to be the most important thing. Right? And precise termination. So correct installation of the cable, precise termination of the cable that connects. Because bad installation is going to do this to us. It's going to pull down the size of the pipe, and the amount of water or data that we can push through there is going to get slow. Right, so let's have a look now at twisted pair cable. So what it is a form of wire in which two conductors are twisted together, and this is for the purposes of cancelling out electromagnetic interference. That interference is going to be either from external sources or between different pairs in the same cable. If you look back at the history of twisted pair cable, originally in the 1800s we had Morse code, which was transmitted across telegraph lines. And back then we were looking at very low rates of data, so they just had two wires that were strung out a long distance, and then they sent these signals across the wires. What happened though, when they started to bring electricity online, they were running electricity on the same telegraph poles. And what was happening was the electromagnetic forces from the electrical cables was causing interference on the telegraph lines. So it was inducing voltages, and that was disrupting the telegraph signals that were running along the lines. So what did they do? They twisted the wires once every few poles. They twisted them over. And what that did was it put the signals 180 degrees out of phase. So the twisting of the wires decreases the interference. And it's the same result as subtraction. If you've got positive and negative voltages and you swap them over, the positive and the negative changes, and so they cancel each other out. And they call that differential mode. So as installers, differential mode is the thing that you will most affect in the cable. Whether it's termination of the cable, whether it's bad installation practices, it's all going to affect differential mode. Right, so we'll take a closer look at it so we can get a good idea in our mind of what happens. Let's say we've got 4 volts, and we're putting 4 volts across a twisted pair cable. Right? So what we want to see at the other end is that same 4 volts. And if we get an imbalance in there, then we're going to have corruption of our signal. Voltage in equaling voltage out means no corruption and no drop packet. But let's say we've got our electrical line or some kind of external interference, and that interference is going to introduce another voltage into that cable. I say 1 volt and 4 volts, it's actually probably a lot lower than that, but this gives you a good reference point. So the more interference we induce, the more potential difference we get between the two sides, and that causes corruption. And I'm sure you know how Ethernet works, right? And if we get drop packets, we get retransmissions. Continual retransmissions means slow down network speed. So how do we do that? We twist it around. So what we are now introducing into there is positive voltage, and because we swap it around, we get a negative, and we get a positive, and we get a negative. And at the other end, we end up that's still that same 4 volt potential. Okay. And this is effectively what differential mode does. So the twisting of the wires is doing that cancellation of interference. So how else do we deal with induced noise on a twisted pair circuit? There is another way, and it's called balanced line transmission. Differential mode is the greatest one, then we have balanced line transmission. And balanced line transmission is something that's not really done by the cable, it's done by the transmission and receiving equipment. So what we're trying to do is balance out the voltage imbalances that can be put onto the line. So what is a balanced line? If we have a look at, say, a coaxial cable, which is unbalanced, if we have, say, a 4 volt at one end, and we get an induction of a volt at the other, then we get 5 volts. So that's an unbalanced line. But if you've got transmission equipment, which is now splitting that 4 volts between -2 and +2, we've still got 4 volts. If we induce the 1 volt into there, as we come out, we've gone to the +2 and increased it to 3, and the -2 increased it to -1, but we still have that 4 volt in between the two. So we're balancing out the line, stopping that retransmission of data. In the old days of data cabling, when I first started out, I started installing cabling in the 80s, late 80s. We had many different types of cabling mediums. So we had twisted pair, wasn't necessarily twisted pair to begin with. We had thin net, thick net, twin X, type 1, type 3. There was a lot of different types of cable. And the only way to balance them all out is to use balance at each end. Okay, so balance the transmission media onto the different type of cable system that we're using. So if you ever come across something that's been called balance, it just refers to the balanced and unbalanced system. You probably won't see these out in network land today, but some of them might still exist somewhere. But pretty much they don't exist anymore. So in review, we've got differential mode, that's twisting the wires to cancel out the interference. We have balanced line transmission, which is to reduce difference in voltages. We also have something called pitch and twist for cable. So we have different twist rates for different colours. And the reason why we have different twist rates is so we don't have it's putting the different twists or different pairs out of phase. So we don't get that same reduction between the two. Colour coding. Right, so if you've ever wondered why we have the colour coding that we have in twisted pair cable, it's quite simple. And it's always going to be blue, orange, green, and brown, so twisted pairs. We use 4 pairs for four pair twisted cable. And the reason why we have that is because it's taken from the AT&T twisted 25 pair twisted color code spec. And if you've done installation years gone by where you were doing voice installation using bulk cables, you quite often have 25 pairs. So they start with the white, and it goes blue, orange, green, brown, slate, and then you go leading red, blue, orange, green, brown, slate. So we're just taking the first 4 pairs from that. What you will notice is that the first pair is blue. But on an RJ45, or say an RJ45 plug, if you look at it, it might lead with the orange pair, or it might lead with the blue pair, green pair, depending whether it's 568A or 568B. When it comes to referring to pairs and cable, if I said to you, we've got an open circuit on pair 1, I'm always referring to blue pair. If you use wire map testers, which has coloured lights which cycle down, testing the different pairs, if you have an error come up on, say, the third pair, it's going to be the green pair. As long as it's a T568A connection.
Can you repeat again this slide? Maybe this slide that you don't understand.
Right. Did everybody understand?
I think they did not understand this slide.
Okay.
Especially for wire mapping.
For wire mapping, okay. Well, we'll talk a bit more about wire mapping when we do testing. But wire mapping is testers which actually cycle through each pair. So they're testing for connectivity between each pair on each positive and negative side of that pair. And it will show up things like if the pairs are reversed at one end, if they're open circuit, if they're closed circuit, if they're reversed with another pair, and it picks up through the wire map test. I'll show you when we do one of the workshops, we'll use some wire map testers, so you'll be able to use them and see how they work. So, color coding when it comes to Ethernet. Original Ethernet was using pairs 2 and 3. So we use the orange pair and green pair for Ethernet. Of course, now we get 4-pair transmission, but typically we'd be putting Ethernet across orange and green. Pair 1 was used for voice, because back when we did a lot of voice cabling, we always picked the white and blue for terminating the cable. Now we'll come to RJ45 pin numbering, because even though their pairs are 1, 2, 3, and 4, where we place the wires are completely different. So we have 8 pins in our RJ45 plug, but we don't start with the blue pair. We have 2 different color coding specifications that we can use. Around the world, different countries tend to use different specifications. Which one do they use here? B. Okay. In a lot of Asian countries, in the Middle East, they tend to go for B. In the Americas, Pacific, they tend to go for 568A. 568B was actually the original specification. So it led with the orange pair. So when they worked out the twisted pair structured cabling color codes, they took an 8-pin RJ45 connector, and then they were looking at the other connectors which they used. So they had RJ11 connectors, which were 6-wire connectors. They had BT style plugs, those, they had the centre two pins carrying the voice. Right, so they said, well, if we're going to upgrade the cabling system, and we've got phones which are using a transmitting pair on the centre, we need to have our voice going through on the centre two pins. So for an RJ45, it's going to be pins 4 and 5. Because in the early days of changing over to twisted pair cabling, they would take a phone plug, chop it off, and then put an RJ45 into the middle. So it all still worked.
Need to repeat again. I think they did not understand this. Why it is RJ45? Why we are using 4 and 5? Building the cable system.
Why we're using 4 and 5 for the blue pair.
Yeah. Why?
That's because originally voice cabling always used centre two pins. So, and voice cabling was using RJ11s and BT style plugs, different 6-wire plugs. And so when they designed the 8-pin plug for structured cabling, they had to keep the transmitting pair for voice on the centre two pins. And that was our blue pair, pair 1. Then they said, well, we've got left 1, 2, 3, 6, 7, and 8. So they said, right, well, let's put our first transmitting pair for Ethernet on pins 1 and 2. And our next pair after the blue pair was orange. They said, right, orange is going to lead on 1 and 2. That left us with 3 and 6. So they split that first pair over 3 and 6. And then that left us with 7 and 8, which predominantly was unused at that point. So that's why we have Ethernet going over 1, 2, 3, and 6. This was our original specification. It was called T568. And then in 1995, when they revised the standards, they brought in T568A. So the EIA, TIA Standards Authority said, right, we're going to lead with green pair instead. And you had different organisations saying, we don't want to change the specs. So they said, right, let's have 2. Predominant 568A, and we'll keep the old one and call it T568B. Right, so what it means in these two is simply that pairs 2 and 3 are reversed. And it doesn't really make any difference because you're reversing them at each end. So that same specification is the same at each end. You test pin for pin, 1 to 1, 2 to 2, 3 to 3 at each end. Doesn't matter if you're leading with green or with orange, if you're doing it the same at the other end, it's going to give you a straight through connection. Is there an advantage of using one? Not particularly. It really doesn't make a difference. It's a personal preference. But of course, we stick with the predominant cabling spec for that country, because otherwise you might have somebody fitting off the patch panel and somebody else fitting off the jacks, and they're both doing different specs, and then you're going to run into problems. So we keep the one type. Okay, so can anybody tell me what the name of the noise cancellation using the twist and the UTP cable are? You remember this?
Noise cancellation cable without
Starts with the D. Differential mode. Okay. So twist rates in cables with twisting wires is differential mode noise done to. And the noise for cancellation using inverse voltages is balance line transmission. Right, so what I'll do is I'll quickly go through the telecommunications standards, just so you're aware of the different standards that we use in structured cabling. The purpose of the standard is that it's a document that sets out specifications specifications and procedures designed to ensure that a material, a product, method, or service is fit for its purpose and consistently performs the way it was intended. Our telecommunications standards were mostly written by manufacturers. So the original manufacturers, the Systemax, the AT&Ts, the Molexes, they all had part in writing the original standards. There was also input from educational institutions, from certain other standards bodies, but by and large, it's the manufacturers who wrote the original standards. What are the specific purposes of having the cabling standards? Well, firstly, it was to support the multi-vendor environment. It enabled uniform planning and installation. It established performance and technical criteria. And if we have a look back at the way telecommunications cabling was in the early 90s or late 80s, we had probably 7 or 8 different cabling systems, main cabling systems. And installers had to know how to install all of them, had to know how to test them, troubleshoot them. And it was also a problem for manufacturers because if you were manufacturing cable components, you don't want to manufacture components for 8 different types of systems. So you had IDM Type 1, they focused on those. We had twin axial cable connectors, things like that. So what they said is, what about if we had one common type of connector? So you could have a connector that was made by one company, a patch panel that was made by this company. You could connect them together because they use a standardized connection, an RJ45 connection. Then it was going to work. So that's what they meant by multi-vendor environment. That opened the door for manufacturers to actually be able to sell product to a lot more people. So what's the scope of the telecommunications standards? We're setting minimum and maximum requirements, things like length, temperature, minimums and maximums, tension on cables, things like that. It's all carried out through the standards. Media parameters. They had there what sort of media we were going to use and how we would connect to that media. Topologies and practices, whether it was star, ring, or bus topologies we used for our cabling systems, whereas now it's more star topology. But back then, we were still using ring and bus topologies. And it set distance limitations for cable as well. So, for instance, with twisted bed cable, it's a 19 metre horizontal length. And it set the connector and pin assignments, like we said before about the T568A and T568B. There's 2 main communications cabling standards that people use around the world. One is the ISO standards, the 11801s, and the other is the NCTIA 568 standard. So in Bangladesh, which standards they tend to use?
The last one. TIA 568E.
568E. Yeah, so in a lot of countries, Europe, I think South America, they're using 11801. They're essentially the same. Okay? They have some differences in the test parameters that they use, but essentially they both use the same sort of standards. So we'll concentrate on the 568 standard here. The latest ratification on the standard is 568E, and that was ratified back in 2022. Every 5 years, they are mandated to either update or put out addendum to the standards. So So that's when they will say, right, you're going to release a version of, say, 568D, or are we going to fully increase it to 568D? And within that revision, they will bring in different things that have come online. So for the 568D and E, we had things like the naming changes, the changes that came in. And they were swapping around the way that they actually referred to this. Some of you who know paving standards might remember that they called it, say, 568.2-B or .C. But when they came to the D, they said, right, well, it's the letter that we're changing, but the letter's sitting in the middle. So they go, they actually got 2. And said, right, we're going to change this around. It's now going to be 568.2-B. So that's all they changed now, this number on here. They brought in things like slimline patch cables, which are now in the standards themselves. So they were recognising 28 gauge patch cables. What else? The biggest thing that came in with that addition to the standards was recognising that using slimline patch cables can affect how much cable you can install in the horizontal link. Because you're using a higher gauge cable, which is a thinner wire, it's going to cause greater losses in that cable. So if you're going to use 10 meters or above of this cable, you have to shorten the maximum length of the horizontal cable to install. And that was all put into the new standards. They're also not suitable for POE. They brought in the NPTL, modular plug terminated link it's called, also called field terminated plugs. We're going to do some of these today. So the field terminated plugs were brought in for direct attachment to twisted head cables. The main reason for having them is they're a much more rugged plug than a standard plastic RJ45. And if you're in certain industrial settings or you've got cables in the ceilings, you want to connect up to wireless access points, you want a more robust plug, you're more likely to use something like this. They brought in category 8 into the new standards as well. So beforehand it was just an addendum to the standards, now it's actually part of the standards itself. The biggest changes with category 8 is that it didn't follow the same standards as, say, Cat 6, Cat 6A, Cat 7, which were 100 metre lengths. Cat 6A is a 30 metre length, and we don't run over 30 metres of that cable. The reason for that is that the cable just can't handle this. It just can't handle that length. When they designed category 7, category 8, they looked at the size of cable they would need to have to run 3,000 megahertz out over a 100 metre channel. And the cable was so large that it just wasn't practical. So they said, instead of making much larger cable, we'll just bring down the maximum length that it can run across. I might go back slightly. If you're going to be going through the 568 standard, sorry.
What will be the places we will get
The place to implement. Category 8 cable is really only a data center cable. got to look at the applications we would want to run 2,000 megahertz. So we're talking 40 gigabit channels. And if you were wanting to run that in a commercial environment, you could only go 30 meters. You couldn't run a cable longer than that. And a lot of cables in commercial environments are longer than 30 meters. So its real only application is in data center cables. You could say that, well, what's the point of actually even using category 8? Might we just stick with fibre? And that's a good argument. It's probably the reason why category 8 isn't really taken on. And it's a very tricky medium to get a full channel working on. So I don't really think it's going to become a big step up, not like Cat 6A was. Does that answer it? In the 568 standards, it's actually broken down into 4 distinct parts. We have the 568.0, 568.1, 568.2, and .3. And I'll go through now which each of those ones is. Oh yes, that's another thing that was brought in with the latest standards. The latest versions of Power over Internet, the 802.3bt, which is, I think it's the 4 PPOE, that's running up to 90 watts across on the POE channel. 90 watts. So we'll talk a little bit about that later, the latest versions of POE and how we run cabling differently when we're utilising it. Alright, so here we are split into 4 different types. I'm actually using the 568.0-D here, not the -E, because that's only recently been upgraded. The initial one was the 568.0-D, and that was generic cabling. So anything to do with generic cabling, whether it's in commercial setting, an industrial setting, health, education, domestic, right? Things that are the same across all those different industries go into the generic cabling standards. So that's dealing with things like the generic topologies, length of cable, recognised cabling that we use, all the installation requirements, full tension, bend radius, cable termination, things like that. That's the same whether you're, whether it's a healthcare facility or it's a commercial setting. The 568.1 is when we start to get into commercial buildings, and that's where structured cabling really comes in, because we start breaking commercial areas into different subsystems. And we're going to look at subsystems soon. But we have things like entrance facilities, equipment rooms, communications rooms, backbone cabling. They're different subsets of a structured cabling system. And each one of those has certain requirements under the standards for it to be considered as a structured cabling system. 568.2 is for the cabling components. It deals with things like permanent links or channel links, gear assembly and color codes. It deals with all the performance parameters that we use for testing. And the 568.3 is all about the optical fiber cabling components. If you do want to get a copy of the 568 standards, they're about $400 US. But if you go out onto the internet and you type in the fancy TIA 568 into Google, and sometimes I've gone to .edu, something an educational facility, sometimes you'll find these things out there sitting on somebody's document circles on it. Or you might find the documents on script. Does everybody know script? Yeah. It probably won't be the latest ones, but it'll have the majority of the information that you need. So that's the 568 standard. Then we have something called the 569, still NCTIA. And 569 is in revision E now. That is for commercial building, telecommunications, pathways and spaces. So it's got to do with setting up pathways for cabling, whether it's conduits or cable tray, ducts, risers, how you actually set them up, the size of the cables, the amount of cables you can put, so the size of the cable trays. All that information is included in the 569. So it's not the actual cable, how you install the cable, it's the platform that you put the cable on. We'll have a look at the 606. Now, you probably wouldn't ever come across the 606 unless you were dealing with large scale installations. If you're installing cabling and you want a numbering system, a lot of the time you'll just number them. It's 100 outlets, and it'll be 1 to 100. Or the customer might give you I want you to number them 1A, 2A, 3A. But when you're dealing with universities or big installations across a wide area with maybe up to 10,000 outlets, you need to start breaking down where cabinets are, where cabling grids are. Different buildings have different numbering standards, and if a customer said, I want you to put in a cabling identification system that's standardized, you would then go to something like 606. So that's going to tell you how to number cable routes, how to number cables in different environments, down to labelling trays, ducts, all that sort of thing. And so it can be standardized, you can create documentation, then you can handle that over to your customer. And they can hand it to someone else who looks at it and say, right, this is following the 606, that means this goes to there. So, okay, so they can apply the same standards to that administration system. But like I said, unless you're doing large scale installations, you probably won't come across it. And the fourth one is, these are the main standards that we use. The fourth one is 607. And 607 deals with grounding and bonding and cabling systems. Now, does the installers here, do you ever do shielded installations? Shielding hospital? So you do grounding systems, or you don't do grounding systems? No? Right. I don't know if we'll have time to go through grounding here today, but the telecom building and grounding requirements are what you would use if a customer wanted a standardized bonding and grounding system. So they're putting in, say, shielded structured cabling. It's going to tell you where your main grounding point should go, how you actually connect on to a main grounding system, the size of cable that you use for your grounding environment, bonding between different points. All of that's covered in that standard. You'd be surprised at the size of the cables that you need to use for a proper grounding and bonding system. Section. So grounding bonding overview, components that you use in grounding bonding systems, and how you do your bonding within entrance facilities and telecommunications routes. So can anybody remember what the standard for the pathways and spaces is? 5, 6, 9. Okay. It's probably good just to keep that in your mind or write it down, because I'm going to be asking in the test probably a question about which standard is which. So 568 is our telecommunications cabling standard. I was kind of hoping you all had laptops with you today. Good? Yeah. Okay, so classes or categories. And this will come down to which standard that you use, whether it's the ISO 11801 standard or the ANSI TIA standards. Have you ever heard of table referred to as class? So class E, class EA. Do you use that here or do you use category? Use category. Okay, so in countries where they use the ISO 11801 standard, they don't refer to tables as category, or they should. It's funny that they actually do. They're called classes. So class D table is Cat 6. Class D is Cat 5E. Class E is Cat 6. Class EA is Cat 6A. And in NC we use Cat or category. Now, when we talk about categories of cable, if I said a cable was a Cat 6, would you say it was a gigabit cable? Would you say a Cat 6 is a gigabit cable? A lot of people refer to it like that, but actually a Cat 6 is not a gigabit cable. It's actually a 250 megahertz cable. It just means that 250 megahertz transmission equates to about gigabit transmission. Cat 6A is rated to carry up to 500 megahertz, which is equating to 10 gigabits. Cat 7000, Cat 8.1, 2000 megahertz, or 8.2, which is a different type of connector. And then come down to 100 meg for Cat 5e, which is 100 megahertz. So you can actually run 500 megahertz on Cat 6 cable. It's just not going to go as far because the higher transmission rate, the frequencies, are going to cause attenuation of the signal, and it's going to mean it's going to lose signal a lot sooner. So you can only run 500 megahertz or 10 gigabits over a Cat 6 cable to a certain distance. Then we look at different types of cable or screening. The industry acronyms used to be UTP, STP, FTP, but now we tend to use this naming feature here, which is the outside area of the cable and then what's around the actual twisted pairs themselves. So now you would say UTP or an unshielded, uncoil wrapped, unshielded twisted pair. Okay. So inside that we have different things like an uncoil wrapped, unshielded and coil wrapped twisted pair cable. So we have coils around each pair, but we don't have anything around the entire cable. Then we have things like FUTP, which is a coil around the entire cable, but nothing around the individual pairs. And we get a couple of different types of shielding, but that doesn't really get used much. The next one step up is usually a shielded core wrap twisted pair cable. And predominantly, always be shielded for twisted pair cable. If you want the best type of noise limiting feature in, say, a Cat 6A cable, you'd probably go for a shielded 4-wrap twisted pair cable. Although there's two different other types that you can use, which is our foil-wrapped, unshielded 4-wrap. So foils around each pair. That's dealing with high amounts of interference between pairs in the cable. Or if you were just dealing with, say, interference from outside, so you might have an environment where there are a lot of electrical motors or machines, and so you might have a lot of electrical noise hanging around. You just want to shield the cable itself, then maybe you just go for a coil wrap unshielded cable. So, Cat 5e, you can get these in coil wrap unshielded twisted pair cables. Not very common those. This one here is a shielded coil wrapped, unshielded twisted pair. So you've got both a braid and foil around the exterior of the cable, but nothing around the pairs. Something that you would use mainly in a high radio frequency environment, might be for running up aerial transmitter pole, something like that. So you want to get a broad range of interference correction across a range of frequencies. This is a shielded 4-wrap twisted pair cable, and notice the twisted pairs on there. So this is a Cat 7 cable, and it's got quite loosely wrapped pairs. Whereas we look at an unshielded, un-4-wrap twisted pair cable, we've got high twist pair rates. You'd think to yourself, why is a Cat 7 cable got less twists? It's high frequency, you'd expect it to have more twists, which would be more interference. Why do you think there's a difference? Alright,
EAMF.
it's to do with EMF, yeah. But because this cable here doesn't have any protection between the pairs, we need a high amount of twists to carry out the differential mode. Okay? So that's that error correction. But when we come back to here, and we have a coil around each pair and a shield around the outside, we've got very low interference between the pairs, so we don't need to have as many twists. The requirement for differential mode is right now. So you'll always find these cables, even though they're running high frequencies, they don't have that high twist.
How can you differ Cat 6, Cat 7, or Cat 6A physically?
How can you recognize?
Recognize or differ, separated from each other, Cat 6A, Cat 6, and Cat 7.
Right.
How can we differ? Beautifully. I'm talking about beautifully. Both C and two together. Cat 6, Cat 6A, and Cat.
You won't get UTP cable in Cat 7. Okay, they're always shielded for that twisted pair cable because they're up to 1,000 megahertz. But
Is there any difference between copper thickness or
yeah. Category 6 is predominantly 23 gauge, so 23 AWG, period wire gauge. You can get 24 gauge at 6. We do it 24 gauge, but you're going to get better performance with 23. Cat 6A has a 22 gauge, so it's slightly thicker. And I think the Cat 7 is 22 as well. But of course, the shielding for Cat 7 is always shielded for wrap.
Yes.
Whereas with Cat 6A, you can get Cat 6A in an unshielded for wrap. It comes in different types. When we get further on, So let's have a look at generic telecommunications cabling standard now. So this is how we look at the structure of a cabling system under the 568 standards. Firstly, we look at, say, our structure of a generic cabling system. And in that generic cabling system, we're going to have different distribution points. So we're going to have a building distribution point, otherwise known as BD, where if it's multi-floor building, we might have floor distribution points. We're going to have telecommunications outlets, which is outlets on the wall. It could be a multi-building environment, say on a university campus. So we could have campus distributors, which is distributing out to different buildings. So we have to actually start giving these things actual structural identities. And so if we have a building and we've got our main distribution point, that's going to be something like a server room. Okay. So a server room for a multi-story building is going to say be on the ground floor. That's where our main cabinet is and our servers and switches. And that's going to feed out to our different floors. On our different floors, we're then going to have floor distributors, which we might call our cabinets, on each floor that we link from the building distributor up to. From the floor distributors, so cabinet on the wall, we've got our patch panels and we run our cabling out to our outlets. That's our telecommunications outlet. And inside these, we can have things called consolidation points. Now, I'll talk a bit more about consolidation points soon. The consolidation points are essentially where we've got our cabinet, we're running a line through to an outlet, but we've got a break point in the middle. So there could be 50 cables running to an office area where you've got multiple desks, and you might want to move them around, and so you put an intermediate patching point in. So it's not active, it doesn't have switches, but it enables you to move cabling and readjust it and change it around or run new cables without having to go all the way back to the patch panel. They call them consolidation points. One thing to always remember though is you can only have one consolidation point in this link. You can't have multiple consolidation points. The reason for that is each time you have a physical break in the cable, you're going to have return loss and reflections at that connection. So you increase return loss each time. So you have to try and keep that down as low as possible, maybe 1 hour. In between these different distributor points, we've got the cable that runs between them. From our floor distribution to our telecommunications outlet, that's going to be our horizontal cable. So essentially, a 4-pair twisted cable, whether it's UTP, Cat6, Cat6A, 4-wrap cable, that's our horizontal cable. But of course, when we're running between building, floor, and campus distribution points, that's going to be referred to as our backbone cable. That's another way of describing that layout. So we've got campus distributor feeding out to different buildings. We have our main distribution point here. We're feeding out to different floor distributors, and then we're doing our cabling out to the telecommunications outlets. In the standards, they have a graphical representation like this. So we have, let's say, our equipment rooms, which is essentially our building distributors. We have our consolidation points. We can have one in between there, we can have one in between there. Our communications rooms for floor distributors, and then our outlets. And this is how they refer to each other. Probably don't need to know too much about that. I'll take pictures of it. I'm not going to ask questions on it. Alright, so backbone cabling. So the backbone cabling is what runs between our campus building and all distribution points. And now we'll look at structured cabling itself. So that was a generic cabling system under 568.0-B standard. So what is structured cabling? It's a set of cabling and connectivity products that integrate voice, data, video, and various cable management systems in the building, such as safety, alarm, security, access, energy, all those sort of things. Back in the early days of cabling, when we were putting in these multiple systems, we'd be running telephone wires, maybe 4 or 6 wire cables, and putting in telephone points, and then we'd be running a cabling system. And then years later, or 2 years later, they might upgrade, say, from an IBM system to might be a token ring. They might upgrade to AS400, so you have to put in twin-ax or a different type of cabling system. It wasn't unheard of back then to hop into a ceiling and find 3 or 4 different cabling systems. You know, the new cables would run in the new cabling and just leave everything that's up there, so there's cable everywhere. And so anytime someone would upgrade their servers or their application, whatever, they suddenly have to run a new cabling system to carry that data. So they said, right, let's develop a structured cabling system that's going to carry the same data or different data across the same system. What are the advantages of a structured cabling system? Well, first, it's standardized. Cabling infrastructure is the same, always RJ45 flux, always the same type of connection that we do between them, same type of cable, 4-pair twisted pair cable that we use. It's going to support voice and data because our pinouts allow for voice to run across there and Ethernet. Allows easy moves, adds and changes. So the standards aren't just there to allow for transmission of data and the performance of that data. They're there to allow latency in the system so that you leave enough space for a customer to put in more cabling in the future. The standards, when they say, or the 569 standard lays out cabling trays and how large a cable tray has to be, it always says that you should fill it 30% full. So you need to leave 70% space. And what that is for is allowing you, the customer, to put in more cables without this installer coming back and saying, right, you're going to put your tray in now. So allowing easier moves and changes. Upgrading the different network types, probably not really that important nowadays, but in the distant past, we can put in twisted pair cable. Originally it was category 3 and then category 5, category 4 and then category 5. And they could put balance on the end. Remember I was talking about those balance, unbalanced connectors? So if it was an AS400 system, they could put in twisted pair cable in the structured cabling system, put on balance at each end, keep running the old service, and then back then, let's say Windows NT, the original version, comes out, that was using Ethernet. So all they have to do is take the cables out, put in patch cords, and connect up to network cards, and they can use the same cable because it was standardized. So let's have a look at these architecture. The 6 main components to a structured cabling system in a commercial environment. It's broken down into entrance facilities, equipment rooms, telecommunications rooms, backbone cabling, horizontal cabling, and work area components. So whatever part of that system is being installed, it's going to fit into one of those areas. Entrance facilities. So let's take a building as an illustration, and an entrance facility is where we enter the building, where the building interfaces with the outside world. It could be where you've got fibre coming in, fibre's terminated there, and then it might be running off into a distributed indoor fibre, or it could be transferring onto XXA or whatever. You could have your telecom IDS there, so running the old style analog voice service. But it's that transition point from external to internal is always our entrance facility. So it contains cables, demarcation points, connecting hardware, could be protection devices, surgical protectors. Connections to the external network provider, campus or building backbone cabling, and then coming through the transition point from the external to internal cables. The standards does have certain requirements when it comes to these different subsets of a structured cabling system. And although some of them you can probably get away with, some of them you really have to make sure that you do. But some of the should be things would be like an entrance facility should be clear of dust, should be clear of moisture. It shouldn't be overly flooded. So underground, might be an underground room where ducts are coming in, and if the ducts get filled up with water in that flooded room, and you've got analog block circuits and electrical equipment, that's going to be bad. There's a lot of dust lying around, and you've got terminations, copper terminations, punch down blocks, that's probably going to cause problems as well. So it needs to be clean. Then we have things like the equipment room. So the equipment room hosts the equipment which serves users inside the building. What you would commonly refer to as a server room. It's an environmentally controlled centralized space. It's going to hold your telecommunications equipment, UPSs, switches, routers, servers, commonly found inside an equipment room. That's what we refer to in the generic sense as a building distributor. So where we have those campus building floor distributors, that building distributor area is going to house an equipment room. So it serves the use, it serves the building as a whole. Okay? All the users inside the building are connecting down essentially into that point. It can act as a telecommunications room as well. So it can act also as a floor distributor. So if we look back here, if we had a building, let's say this office here, look at one floor, the main cables come in to where the main server racks are, and you've just got the users on this floor. So you're not going to put in a separate floor distributor, you might as well just run all the cables from that main cabinet. So that main cabinet is essentially a building distributor and a floor distributor at that point. Grounding and bonding facilities come down through here in an equipment room. So we look back here, if we've got grounding and bonding going on through this building, they will eventually come down onto a main grounding bonding point in here, which then bonds through onto the electrical system. Should be centralized in a controlled environment. So it makes sense for things like floor distributors and building distributors to be in a centralized point. Primarily because cables are running out from there. If you've got a massive area and you're putting your server room right down in one corner, you're having to run all this cable out to all those long points, then put it in a more centralized environment, and then you don't have to run so much cable. Backbone cabling. So backbone cabling is all of those points between campus, building, floor distributors. Provides the interconnections between the telecommunications room, equipment room, main terminal space, and the entrance facility. It extends between buildings in the campus environment and mainly consists of fiber nowadays, but you can use Cat6, Cat6A. It just gives you a lower amount of bandwidth. If it's in a, let's have a look here. If it's in this environment here, so our backbone cabling between our building distributor and our floor distributor, I'd be quite happy for you to use copper cable if you wanted to. If it was between a building distributor and a campus distributor, I would say don't use copper cable, use fiber. The main reason for that is potential differences in burning. A lot of the time, this building is going to have a separate electrical system for this building, and the potential difference between earth is going to be different, and that's going to cause problems on a electrical-based system like copper. Fiber, of course, it doesn't matter. It's involved in life. Backbone cabling under the standards also gives you maximum distances that you can use. So for a building backbone cable, you can't go more than 500 meters max between building distributor and floor distributor. You'd have to have some kind of intermediate point in place. If we're talking about campus distributors, for it to actually be part of this generic cabling system, you can't go more than 1,500 meters, or else you're moving outside that definition of what is the land, the local area network. So you might be now talking about a campus area network, or a metropolitan area network, or a WAN, but it's no longer a WAN. Yes.
If it is building distributor to full distributor, is the 500 meter max? Can you use the?
No. Because you're still it's saying 500 meters max, but of course if you went out to 500 meters, you'd have to be using fiber. You can only go 90 meters if it's physically packed. I'm going to talk more about it before, but if you're thinking 90 meters, why is it 90 meters? Shouldn't it be 100 meters? Yeah, the standards allow for 5 meters of patch cord at each end. Right? So they say that's a channel link. Channel is from patch cord to patch cord. Permanent link is between patch panel and outlet. And everything in between there is the horizontal cable. So horizontal cable is what's in the wall and in the ceiling, and that can never be more than 90 meters. If it is, then the test is going to fail. Use link testers. Alan. Should use start topology. So start topology means you have a central point and you're running one connection out between, not looping, not running a ring topology. And it's always in start topology now. Bridges and taps, you can't put break into a cable that's a backbone cable, so you wouldn't normally do that if it's fiber, but if it was say Cat6 or Cat6A cable, you're running from your building distributor to your floor distributor, and you only needed pins 2, 1, 2, 3, and 6 for your Ethernet, and the security guy says, oh, hey, can I take ground here and use it as an analog line? Okay? You're breaking into the backbone cable and potentially introducing noise. So no bridges, no taps. main and intermediate cross-connect jumble or patchwork links should not exceed meters in a backbone cable. Elevator shafts never would be used. I know it seems pretty obvious, but it has been done before and it's never a good thing to do. Total maximum backbone distance 90 meters if you're using copper. Now, we move on to the support subsystem, which is our telecommunications rooms. And our telecommunications rooms are our floor distribution points. Now, when we talk about telecommunications rooms, we're not talking necessarily about a cabinet on the wall. We're talking about a designated space for that cabinet on the wall. So, quickly, a room here that's been set aside, that's where the cabinet goes. That cabinet is our floor distributor. And that floor distributor sits inside the equipment. But it could also be a cabinet on the wall. It's just not a telecommunications room, it's just a floor distributor. And so, when we talk about structured cabling, you don't necessarily have to have a telecommunications room. But if you do have a network where they designate the floor distributor is going in the telecommunications room, that's when you come to our structured cabling system, and standards will tell you minimum sizing for your room, heights of doors, all that sort of thing. Amount of light that's in there, amount of electrical, all that sort of stuff. So it's where various telecommunications and data equipment reside, connecting the backbone and horizontal cabling subsystems. So, yeah, it sits at the floor distribution. And telecommunications rooms should not be located in any area that could be affected by excessive heat, humidity, or flooding. That makes perfect sense, because those rooms are likely going to have patch panels and connections and electrical equipment, switches, routers, wireless access point. Should be set up in such a way to allow the housing of the telecommunications equipment. So there should be enough space to have a cabinet. Electromagnetic interference issues will be or should always be considered when setting up the telecommunications room. So you need to know what sort of electrical interference is happening around that room. If they designate a room, let's say this room here, they want you to make that the entrance, the telecommunications room. They want the cabinet on the back wall, wall-mounted cabinet, and yet on the other side of the wall there's a great big switchboard, electrical switchboard. So that's going to cause a lot of electrical magnetic interference between that wall and the equipment. So you need to be aware of what's around there. A good way of working out the sizing for a telecommunications room, and you might want to take a picture of this screen, is 0.07 meters squared of TR space for every 10 meters squared of work area space. So, in the standards, it lays out sizing of rooms like this, and the customer says, I want you to designate the size of the room. How big the room is then going to depend on the area of that floor that's going to be used for people. So they say work area space or usable workspace. So the easiest way to do that is to take floor space and work out the area of that floor space and take out 25% for coffee room, toilets, hallways, unusable space basically. So 75% of that total space becomes your usable floor space. So for every 10 meters square, you course, if it's a small area, so we don't have a lot of users, the standards do say what the minimum should be. So they'd say 14 metres squared for a telecommunications room as a minimum. Cable route management, routing, and cabling support such as supporting cables shall be employed for effective management. So cable running in there should have cable trays, cable management in the cabinets, things like that. And if it's an actual telecommunications room, it should be dedicated to the telecommunications function. It shouldn't be the tea and coffee room, cafe, or the room cupboard. It needs to be dedicated to that function. Should be located where there's easy access to cabling pathways, linking to either the horizontal cabling or the telecommunications rooms. Should be based on the floor space that's used. We talked about that before. Technically, it should be environmentally stable. Because you've got a lot of electrical equipment in there, you should at least have good airflow through that room.
Is the degree Celsius for technological room or server?
Both. Well, the standards state that an environmentally stable condition for electrical equipment is about 20 degrees Celsius. So when they say it should be environmentally stable, then they just go back to what they rate as being environmentally stable, which is 20 degrees. That's not a definite, but that's under the standards. They're saying this will guarantee that you won't have failure on this. If you're not going to have air conditioning, the most you would want is some kind of airflow. So you don't get built up heat, particularly electrical. Anybody else? Horizontal cabling. And so this is the cabling that we're running from our floor distribution points out to our end user outlets. Wiring from telecommunications rooms to the outlets on the floor includes horizontal cable, mechanical terminations, jumpers, and cords. May include multi-use telecommunications outlets, assemblies, which are you've heard of mutos? Everybody heard of mutos? I think we have a look at that a little bit further on, so I won't talk about it now. But they basically type of consolidation point. And the maximum length is always going to be 90 metres. People have said to me in the courses that I've done before that, I've run at 610 metres and it worked fine for me. And it may seem like it's working fine, they may be very lucky. But it's set at 90 metres or 100 metres max for a channel connection. And over 100 metres, there's no guarantee that you're not going to start to have that error rate increase and retransmission. So even though your transmission equipment is communicating and agreeing on a protocol and speed, they still might be dropping more packets than you're aware of. So even though it works, it might not be working well. Recognised cabling and horizontal cabling is either a 4-pair, 100 ohm, unshielded or shielded twisted cable, like I used to be. Or you can use multi-node and single node optical fibre for horizontal cable. The fibre has to be at least 2 fibres. So horizontal cabling is what sits here between our floor distributor and our telecommunications outlet. It also is going to include the consolidation node. When I said the combinations like you connect this to patch panel. But then I said jumpers and patch cords. Normally jumpers and patch cords you think are outside of the horizontal system, but then we come in, we look at consolidation points, that's another internal, they might have jumpers between the two, they might have patch cords between the two. So we could use 100 ohm 50 cables, you can use 150 ohm shield cables, you could use OM3, OM4, OS2 fiber cables if you want. All recognise payment. What it doesn't have is any application specific components. So I'm talking here about any kind of resistance, splitters, adapters, components that would normally sit outside and plug into a faceplate. You can't put on the inside, wire it in. Proximity of horizontal cabling to source of beam I should be taken into account. So when you're running your cabling in ceilings or through pathways, you always need to make sure that you've got a good spacing between the cabling and any electromagnetic interference. Whether it's power cables or security cables, you need to maintain a 300 mil distance. That's your minimum. At 300 millimeters, you can guarantee that you're not going to get electromagnetic interference. Each work area must contain a minimum of 2 outlets to be considered as a structured cabling system. They haven't changed that yet, they might one day, but what they're saying is that it can be either 2 twisted pair cables, or it could be 1 twisted pair cable and 1 fibre, but it needs to be 2, or else it's not structured. Yes, there are instances where people will just install 1 outlet, to each user position because they've got IP phones and they're just going to slave their computers on the phones. That's fine, and we'd probably certify it, but we wouldn't certify it as structured, but we'd still certify it as a warranted system. If your customer came to you and said, I want a certified structured cabling system, I want 1 outlet, because I'm going to slave off the phones, you'd say, well, you sure you want structured? Because if you want structured, it's not going to work. So we're not going to get certification. Additional outlets may be provided. These outlets are in addition to and cannot replace the minimum requirements of the standard, which is 2 outlets. Why do you think we would have 1 copper and 1 iron? So they say you have to have 2, it could be 2 copper, or it could be fibre, but it still has to include 1 copper. They're allowing for analog voice traffic, they're allowing DOE as well. So allowing those electrical connections still to be made, because once you're all fibre, you can't utilise that user point to plug in, say, a phone, an analog phone, or a wireless access point that's powered by DOE. So it's keeping that flexibility in the cabling system. Horizontal cabling shall be configured in a star topology. So star topology. Star topology essentially is a central patching point, and you're going 1 cable to each outlet. Bridges, taps, and splices are not allowed in a copper-based horizontal cabling system. And yes, we did used to tap in or tap on cables or join them in the old days. We were doing category 3 and category 5. It really didn't matter that much back then, but higher frequencies it caused some problems. Length is not to exceed 90 metres, and total length connection, including the equipment cable, should not exceed 5 meters. What it's saying, we really shouldn't have more than 5 meters attached cable at each end. Yes, that might be what it's called here, but technically it shouldn't be. So I don't need to worry about these. I'm repeating myself. There's a one here that says the distance between the floor distributor and horizontal cross connect and consolidation point shall be a minimum of 15 meters. What this means is that when you're running a cable, and it could be a cable from a patch panel to 1945 outlet, or it could be a patch panel to a consolidation point. They say that it should be at least 15 meters minimum. If it's only 15 meters or less for the outlet, what I would normally do is I would lose some cable in the ceiling, keep that distance. And the reason for that is, and I explain it more when we do our testing, it's called a short length return loss. What happens is when you get transmission signals at the transmission end, you get nearing crosstalk between pairs. And that nearing crosstalk will keep happening anywhere up to at least 15 meters. At 15 meters, the signal is attenuated enough that it doesn't cross those two pairs. So if you've then got a connection point at say 5 meters, and this power of the signal is hitting that connection point, it's going to be creating more nearing crosstalk. So you're actually amplifying the amount of nearing crosstalk that's happening. So you always try and keep that distance out to about 15 meters. Sometimes it might not be possible, but as a rule, try and keep it to that minimum of 15 meters. Pathways are used in walls are not suitable for cables, solid block walls with no ceiling or underfloor access. That's where we're going to use things like conduits or ducting or some kind of wall trunking. Typically, the best thing to use if you're going to be using round wall trunking is some kind of anodized steel trunking. Mainly because this could be over a certain distance, and we've got electrical cables and data cables running in that trunking, even though they're separated. If it's a plastic trunking, we're going to get interference between the two, because it's quite close proximity. If you're running in steel trunking, that trunking is going to be electrically urged, so you don't get that interference. If it's just ducting that's coming down the wall, you're actually, if your electrical cable and power cables are running close to each other, they're not going to introduce too much interference. Yeah, we can. Normally we would finish, but we had that interruption at the beginning, so, but yeah, let's stop the break. Yeah. When we have 15-minute break, and then we'll carry on. We don't have too much more before we do some workshop.
বেশি বেশি বড় না কিন্তু ওখানে গিয়ে এখন যাবে ওখান থেকে সামান নিয়ে তারপর আসবে এই সবার সবাই সবার
Oh, that's fine. Thank you. Pretty much said yesterday, will they have that? Because they bring up all of that stuff on the screen. That stuff, and then they could. And some of them do, and they want to use. Some of them do have that. I've got a USB stick. Do these people?
সবাই তো
Why don't we get them to get their laptops out? I'll give the USB stick, they can hand it around. And they can bring out like the handouts of this. So when they do their test, they can go back and go, oh, they can check me out. Otherwise, they're going to find it very difficult. Hey.
যে ওখানে প্রশ্ন আপনি নিয়ে আসছে
জি জি
পরেরগুলো আমি আজকে আপনাকে পাঠিয়ে দিচ্ছি বাস ঠিক আছে ঠিক আছে চলে লাস্ট একটা পয়েন্ট বলছি ফ্লোর র্যাক থেকে আমার প্রেসপেক্ট পর্যন্ত যে কেবল আসবে এটা কখনোই 15 মিটারের নিচে হওয়া যাবে যদি হয় উপরে প্রয়োজনে কেবল
ল্যাপটপ
ভালো আছে।
থেকে শিখাই দেন মানে ওরা আমি অনেকগুলো তারপরে এক ইয়ে থেকে আরেক ফ্লোরে উঠাইতে গেলে যে কিছু ইয়ে বললো এগুলো কিন্তু খুব
IPKVM console যেটা আছে এর কি কিবোর্ড আছে এক্সট্রা কিবোর্ড লাগবে আমি কিবোর্ডের এই স্যারের ফোন ওয়ারেন্টি যেমন শেষ বাকি ওয়ারেন্টি না আমাকে শুধু ইয়ারই তো এক্সট্রা কিবোর্ড থাকলে কিবোর্ডের দাম মাইক ভাই কি আইডিবি